There is a persistent assumption in the industry that uploading an image or an audio file into a frontier model provides the system with native, human-like perception. The reality exposes a paradox. The same language generation that makes these models so capable also makes them dangerous when processing visual data. Look at this split-screen interface. On the left, a standard text prompt generates a correct mathematical output. On the right, we prompt the model with an embedded chart. The model returns a beautifully written, authoritative paragraph explaining the graphic. But the text contradicts the specific data points plotted on the chart. The output is fluent but factually disjointed. We categorize these mistakes as either perception failures or reasoning failures. A perception failure occurs when the system cannot encode the pixels in the image. A reasoning failure happens when the encoding is successful, but the language model misinterprets the result. This distinction makes debugging multimodal pipelines more difficult than text-only LLMs. When a medical scan or a financial receipt returns an error, engineers have to determine if the model is blind or if it is simply guessing. Scaling a model beyond text requires solving for representation alignment across the entire pipeline. To understand where these failures originate, we need to build the multimodal architecture from first principles. We start with the core language model block. Mathematically, this system is strictly constrained to process and generate text tokens. On the opposite end of the pipeline, we have the raw input, a dense array of pixels representing an image. Connecting the two begins with the Vision Encoder. This acts as the initial observer, compressing those raw pixels into a dense mathematical embedding. Here we hit an architectural gap. The Vision Encoder's dense embeddings exist in a different dimensional space than the language model's text tokens. To bridge this gap, we introduce an adapter or projector layer. This layer acts as a translator, forcing the visual embeddings into a shape that fits directly into the language model's native space. The language model is blind. It only reasons over whatever visual translation the adapter successfully converts into text tokens. Proving that these separate modalities could exist in a shared semantic space was the breakthrough of the CLIP architecture. This 3D coordinate system illustrates a latent space. CLIP achieved alignment through massive-scale contrastive learning, utilizing datasets of paired images and text. Notice that the vector for the word dog and the vector for an image of a dog start far apart. Natural language acts as a strict supervision signal here. It forces the perception model to pull related concepts together, learning abstract relationships rather than rigid, hard-coded labels. The result is a shared semantic space where text and images coexist and can be retrieved or referenced interchangeably. CLIP shifted the field away from rigid visual classifiers toward flexible, open vocabulary systems. This alignment made generative multimodal models possible. Operating these models safely requires strict visual grounding. The model's language output must remain tightly anchored to the provided image evidence. If the visual evidence from the encoder is ambiguous, or if the adapter projection is weak, that anchor breaks. When this happens, the system typically exhibits a lazy student effect. Instead of admitting the image is unclear, the model falls back on its strongest asset, its language priors. It begins guessing based on what is statistically plausible in its text training data, allowing language patterns to overwhelm the actual visual signal. Ask a model to identify an object in a dark, grainy photo, and it might confidently describe a specific corporate logo on that object. The logo isn't there. It just appeared frequently alongside that object in the model's text training set. In an enterprise environment, these errors are severe. They bypass automated text-matching QA pipelines because the sentence structure is flawless. Without strict grounding enforcement, a multimodal architecture acts as a confident fiction generator rather than a visual reasoning engine. When building production systems, engineers face a choice: extracting visual data using traditional OCR or relying on native vision language understanding. If the workload involves dense, static text on legacy documents, forms, or receipts, OCR remains superior for raw character extraction. Native vision models excel exactly where OCR fails. They interpret complex spatial layouts, evaluate overlapping objects, and detect visual anomalies that contain no text at all. Mature systems do not treat these as mutually exclusive options. They route the data through both pipelines and combine the signals. This dual input reality changes prompting strategies completely. You must explicitly direct the model's gaze. The prompt has to instruct the system on whether to prioritize exact text characters, the physical relationships between objects, or the overall layout of the document. In a multimodal pipeline, the prompt serves as a simultaneous control interface for both language reasoning and visual attention. Scaling the architecture to include time-based audio and video introduces a completely new access of strict alignment requirements. Video forces the Vision Encoder to change behavior. It must now sample and segment sequences of frames, rather than processing a single static grid. Audio presents a parallel challenge. Acoustic features must be mapped and synchronized with language tokens across a continuous time axis. If a user asks a question about an hour-long video, the model must execute complex hierarchical reasoning to connect one localized micromoment of action to a broad text response. Scaling multimodality is an orchestration problem that pushes latency and computing constraints to their limits. Evaluating these systems requires prioritizing grounded correctness over conversational fluency. Testing requires targeting specific visual failures, like hallucinating unseen objects, misinterpreting the axes on a chart, and over-trusting noisy OCR inputs. This flowchart maps the diagnostic process. You have to isolate a perception error, where the encoder or adapter dropped the data, from a reasoning error, where the language model simply misinterpreted it. This matters because real-world production images rarely resemble clean benchmark datasets. In production, success depends on how accurately the system translates visual inputs into the precise language of logic.